Model free last class. What's the main difference between model based and model free? You don't compute t. You don't estimate t. Okay? Instead, you directly go to the value and policy. So you ignore the transition. And as I mentioned last time, if you do not have t, then you can't mentally simulate the world in your head. But you can still be able to reflexively do the right action. And I told you there are cases in the world, such as swimming, where you don't already know how to, you already don't know how to simulate mentally what will happen when you try to make certain various, actions in the pool. You actually just have to do it. Anytime you have to do it, that means that's model free. You don't have transitions. Whereas you don't, suppose you're trying to make a plan to go to like Beijing, okay? You have a model. I understand sometimes planes don't go on time. I understand that sometimes Hong Kong airport might be full of protesters, but it's not that it's completely model free. You actually make some kind of a plan because you have a model. Instead, you don't say, I don't know how to go to Beijing. I'll just get out onto the, the rural road at Mill Avenue and then make a left, make a right, and eventually I'll get to Beijing. Right? That's model-free way of traveling. You see what I'm saying? Which makes no sense, obviously, for us, because in fact we do have reasonable models. So my point is, for some problems there are models, and when there are models, we want to use them. For some problems, it will be very hard to get models. It's not that there are no models; it's that they are very intractable. Okay, and yeah, so for all practical purposes, it's better not to think about models. So this issue of models are there versus not there, actually for the problem becomes a philosophical one. For example, people will take the view that there is no such thing as stochasticity in the world except at the quantum level. Some people will say that. So you, for example, will say, I toss a coin, I don't know what will come, maybe comes heads, maybe comes tails. And some guy with infinite simulation capabilities might say, you're a bozo. It's all well known what the equations of viscosity are, what the equations of gravity are. So if you had some interest, you can exactly compute how many times it will twirl, how many times it will get pushed by various eddies in that particular area, and exactly how it will fall. You decided, life is too short to do that, I will assume it's stochastic. In fact, a lot of times, by the way, people would like to assume that the world is stochastic when they can't be bothered to do the computation. You see what I'm saying? Like, for example, our ancestors will say, sometimes moon seems to be going away. Sometimes sun seems to be going away. Who knows? Obviously, we'll make this guy called God who seems to know everything. And we'll just say, our ignorance means God. And as civilization progresses, God has become smaller and smaller and smaller, hopefully. Because we actually know exactly when every particular eclipse will occur. We don't need God for this anymore. For those of you who still want to believe in God for eclipses, you are basically mentally lazy. I think that's fine. Okay? God you can compute, you should depend on gods. Okay? Okay. So, then anyway, that's the point to keep in mind. But anyway, here, from our point of view, you can, from the reinforcement learning point of view, there's this question of, is there model for the problem, tractable model for the problem? That's kind of an existential question. And in fact, as I said, quantum physics people will say everything has a model. And there is there is no such thing as uncertainty even, except at the quantum level. And there is a question of, do you want to act in the world in a model-free way or model-based way? So we are talking about the second part. An agent can live in the Beijing, travel plan to Beijing world in a model-free way. So for example, it might have compiled a strategy. If it goes to Beijing every day, like you can't go to Beijing every day, I guess, it takes too long. So if you're doing it all the time, then you basically say, if I am on Mill Avenue, then I turn right. Then I sit in this, car that magically appears. Then I get down at this door 4 of, terminal 4. Then I take this elevator, etc., etc. So all of the actions are just baked in, at the end of which you will be in Beijing. Okay, but most of us don't solve the Beijing problem that way. We basically have the model and then we use that to plan in our head, which is much cheaper than actually going, and trying and failing. Okay, so in the case of model 3, instead of learning the transition T, we just want to learn the value of a policy or the best policy without bothering to learn T. Model 3 is most reasonable when in fact learning T is too costly. It's unreasonable if in fact learning T is easy, but you are too lazy to learn it. Okay? But it doesn't matter. You can use the algorithm either which way. And then so the right motivation is that in some cases T is too big. The action done from a state can potentially take you to a huge number of states. Sometimes the space of actions is infinite. So we, as much as we are looking at reinforcement learning in these nice discrete grid worlds, right? That's the one we were looking at, where each cell has exactly 4 actions, okay? And they can only take you to 4 different states. If you start considering basically continuous spaces, such as swimming, right? So you can put your hands in any arbitrary fashion. Some number of them make you sink like a stone. Some number of them make you float. Some number of them also let you go forward. Having an entire model of it is much costlier because at every point in a continuous space, in essence, you have infinite branching factor. Continuous space with continuous action set. Swimming is one of those. It's both a continuous space because your position in the pool can go from, it's not going discretely from grid to grid. And the action space is infinite too. In those cases, for sure, model free is better. Okay? So rather than wait for T to converge, in those cases, if you try to compute T, computing T can be harder than computing the V. Estimating T can be harder than estimating V. So you give up on estimating T and then go directly to estimate V. And of course, once you estimate V, you get pi. Okay, so that's model free. Now, have we seen model free RL till now? Have we at least seen one RL algorithm where we did not estimate T? So I'm talking to myself mostly. The very first algorithm for RL, which is a dumb algorithm, the Monte Carlo, did not compute T. Right? So Monte Carlo is your first model-free algorithm. You already know one model-free algorithm. I'll give you a better one. You guys got it? Anybody having trouble understanding that Monte Carlo is a model-free algorithm? If you don't estimate T, then you are model-free. That's it. That's the definition of model-free versus model-based. Okay? So, you saw the Monte Carlo already. What I want to do is a better idea than Monte Carlo. In the case of Monte Carlo, what we wound up doing is we got huge episodes, full-on episodes, end-to-end, and looked at them and evaluated the U over each of the episodes. What I would like to do is somehow, for every transition, can I update my values? For every transition, can I update my values? That's what I want to do. So imagine the following thing. You basically initialized the values of all the states to V0S. Now you made a transition from, let's say, S to S dash. The fact that when you tried to do an action in S, you went to S dash is valuable information. because it tells you that your value of V0 of S1 should somehow be closer to S2's value, V0 of S2, modulo this action cost. You agree? You didn't know before, but now you know. Remember the reason we thought Monte Carlo is a bad idea? Because it doesn't take into account the correlation between states. Whatever I just said is taking correlation between states into account. So clearly, just like ADP, this method of somehow making your value be closer to your neighbor's value every time you see that neighbor. That's a winning idea. Now the only thing, of course, is let's say V0S is 1, and V0S1 is 1. V0, and then I did an action A in S1 according to the policy pi, and I got to S2, and the V0 of S2 happens to be currently 59. I know that 1 is too low, I need to go towards 59. How fast do I just become 59? How fast do I become my neighbor? I could say, well, really, if I took the action whose cost is, let's say, 4 units, and then I am going into a place which has 59 units value, then 59 minus 4, 55 must be my value. Which is a reasonable thing to say. But for the fact that the action you did is a stochastic action. You don't know how often when you do this action in state S1 will you go to S2. Maybe in fact, unbeknownst to you, the probabilities are that when you do this action A in S1, with probably 10 power minus 25, you go into S2. You just happen to be the lucky guy, and and then because of which you can't, if you just changed your V0 S to be 55, you made too big a commitment. You guys see this? What I'm saying? So you want to throw in a little learning rate. You want to say, I want to go towards my neighbor, but sort of what I want to say is, I'll take this alpha, which is a number between 1 and 0. I'll take 1 minus alpha of my value plus alpha of my neighbor's value, and I'll say that's me. Weighted average. Aren't you getting this rather sinking feeling as to why did I take this course where after about 11 classes we find weighted average, and that's like the greatest idea. Right? This is what I told you. Reinforcement learning algorithms are extremely simple. The interesting part is why do they make sense and under what conditions do they have what properties. Okay? So that's basically so what I did there is I went from S1 to S2, and because I saw that transition happen, I changed the value of S1 a little bit so that it's consistent with that of S2. And this happened in time, right? Basically from S1 I did an action. When you do action, causation always flows in the forward direction. So after some time, basically the time is going forward. And there was a difference in your value because you took action A and went into S2. And you're taking this temporal difference in the values and you're pushing yourself in that direction. That's why it's called temporal difference learning. And the thing about this is T is completely missing in action. There is no T. If in fact this particular transition getting you to state S2 is highly rare, you don't have to worry because it will never again happen, and you will keep seeing that you are actually surrounded by many, many, many poor neighbors. And so eventually you went, let's say, from 1 to 4, maybe because of some alpha learning rate, because you had a 59 neighbor. And then 4 to you go down, 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 down to maybe minus 0.7. The world tells you what the world does. That's what model free does. Basically, model free learners look at the experience and then update their values. Extremely simple idea. Okay? So in this particular case, what we are doing is you are taking, you are essentially taking v pi of s and I'm updating the value of s with respect to pi to be the current v pi of s plus some learning rate alpha times the difference. The difference is my value and the value, the transition plus value of the next state. Because the sample, when I got to S dash, the sample basically is the transition cost, RSA S dash, which is what I was telling you, 4 units cost that I incurred. In this case, it's a reward. Plus, the S dash itself has a current value. That's v pi S dash. And then if you are doing discounting, you also have to throw in a gamma. Because the S dash value will be yours only after one step. And the values one step away is gamma times less than value now. So in essence, the sample, when you were in S and when you did pi S, which is the action A, according to the policy, and you went to S dash, then you got this number, which is basically the sample's value. You subtracted that from what you currently thought is your value. That's the difference that should have been 0 if things are consistent. Do you guys see this? If in fact, if v pi converged, this difference should become 0. So the update is basically making you go towards conversion. Another way of looking at this, if you want to look at it that way, is you can essentially say 1 minus alpha times v pi s plus alpha times sample. Right? Is that correct? No, 1 minus alpha times v pi s, times alpha times sample. It's just rewriting that now. Basically weighted averages. So here's a cute thing. Even though really understanding this, you should understand this already, and you have any questions as to what if I overcommitted, you have to convince yourself that if in fact S dash is one of these lucky things that only happens once in a blue moon, and because of which you increased v pi too much, even with respect to the learning rate alpha, it will slowly come down because again and again S dash won't come. Because the probabilities will work out in the limit. All of these are only supposed to work in the limit. All probabilities are supposed to work only in the limit. Okay? This is basically what this is saying. What if a very unlikely negative or positive transition biases the estimate? Well, it can't bias because rare occurrences are by definition rare. Do you see what I'm saying? As long as you're not brain damaged and think that the one time you won the lottery must mean all the times you'll win the lottery without having tried buying tickets more and more times, you would get, if you kept on buying tickets in the lottery, you would realize what everybody else realizes already, that lottery buying, buying tickets for lottery. If in fact dollars is utility, dollars is value, then buying lottery tickets is a tax on stupidity. You would have realized that if you just let the world be the world. You just stopped after one winning and they say, oh, I'm chosen one. And everything else, oh, that's just a mistake. I'm sure again, I'm continuing to be a chosen one. And then, how many people, by the way, this is true apparently, how many people who won lotteries have died paupers? Look it up. A lot. Because they tend to think, it happened once, I'm sure it happens lots and lots of times. So the next 59,000 times I lose the lottery, I'll still say it's rare. I'm supposed to win. Remember when I was like 4 years old, I won? I'm going to win again. That's how you become paupers. Okay. This is actually a cute way of remembering. It's like understanding that what temporal difference learning is doing is essentially computing moving average. Okay? And this is just basically saying, suppose you have n numbers, x1, x2, etc., xn, and you're computing their average, that's x hat of n, which is the average of the first n numbers. Then now if I get the next number, n plus 1, xn plus 1, then the new average, x hat of n plus 1, would be this. Right? Now, but x hat of n plus 1, which is x1 all the way up to xn plus 1 divided by n plus 1, can also be written as n times x hat of n. This is how, suppose I told you there are 50 people in the class and their average mark is 10, and a 51st person comes and their mark is 25. What is the new average? Unless you have failed SAT and GRE multiple times, you know that it's not 10 plus 15 by 2. Right? It's 50 times 10 plus 25 divided by 51. Remember, I told you how to do GRE. And for undergrads, this is extremely useful. Okay, this is like a random question keeps coming up in GREs because they realize that most people don't understand the concept of moving average. Okay. Anyway, so this is n times x hat of n plus xn plus 1 by n plus 1. We can write that as n plus 1 times x hat of n plus xn plus 1 minus x hat of n, because I basically added in one x hat of n and I subtracted it. Now I can remove this part, it will just come out as x hat of n plus 1 by n plus 1 times x of n plus 1 minus x hat of n. So way of thinking about it is the new average is old average plus 1 by n plus 1, which you can think of as alpha, times the difference between the new sample, which is xn plus 1, minus the old average, which is x hat n. I would argue that's basically more or less the structure of the temporal difference equation tree. Of course, here there is no notion of transitions, etc. I'm just saying the math works the same way because you're computing a moving average. Okay? So, if you must have some kind of an example, here is like a simple world, A, B, C, D, E are the states, you are here, and then I observe, okay, remember in temporal difference, you must observe the transition. When you observe the transition, you update the value. In Monte Carlo, you did the same thing, except you had to observe a whole sequence of transition which ends into some terminal node or something, and then you update. Okay? Here for every little transition you are updating. So originally you started with 0008. Okay? And then I was basically in state B, and I went east, and then I apparently did get to C. And in doing this transition, I lost -2. That's the cost of transition. So because of which, in essence, this 0 should be pushed towards -2. Right? Because the total cost is -2 plus 0. And it has to be pushed towards that. With the learning rate. The learning rate I use is alpha equal to half, and the discount factor gamma equal to 1. So it should be pushed towards -2 at rate half. Sure? It should be -1. Okay? And that's what that one is showing. This basically is the actual numbers being crunched, but you pretty much understood what to do. Now this is the interesting thing. So you go and say, Mom, I learned how to do temporal difference learning. And Mom asks, they show me, and so I add numbers, and then I divide them. And, Mom and Dad will be very sad. But you can then tell them that, Mom, I can get a nature paper soon. And then they'll be happy. Okay. Okay. So that, and then, similarly you continue here. If you go to C from east, then you go to D. At that point, you can prove to yourself that the update for this will be 3. Do you see what I'm saying? Okay. So this is temporal difference learning. For every time the transition actually occurs, it updates. And if it does it enough times, it will basically converge to the same value, optimal value, the value of the policy, because we are following the policy here. Okay? Now the next thing is, now that I have the temporal difference, temporal difference is the model free idea. Can I do, and it's a model free passive RL, because I'm using a policy that's given. You have to get all these terminologies into your head. Passive means you've been given a policy, active means you get to do actions, model free means you don't have T, model based means you have T, discounted means there's a gamma, all this stuff, all this terminology you have to keep in mind. But anyway, if I just went with TD, and I basically, remember the way I went from ADP passive to ADP active, it was almost a sleight of hand. Right, I said I had T, I'm supposed to be just using it to compute V pi, but you look the other side, I computed a greedy policy. I said, I won. Right? Can I do something like that for temporal difference learning where I have the value? Turns out no. Because imagine, here's the very interesting thing. To understand this, imagine you've been, and we actually talked about this once before, but this time it's actually more immediate. Imagine I gave you V star. I gave you V star. And we know that if you give V star, you can get pi star. Can you get pi star given V star in the model free scenario? In the model free scenario, you don't have T. You didn't care about T before. What you have, you don't count. When it's missing, you realize, oh my God, what do I do now? Because if you don't have T, the way you convert V star into pi star, you start at the state S, and then you consider all actions that you can take from that, and compute their expected valuation. That will be in terms of transition function and the values of the neighbors, and then pick the action that is maximum in that expected sum. Since you have T missing, you'll be looking and saying, I have V star, what can I do? There is a Far Side cartoon. By the way, Cow Philosophy is a Far Side cartoon. Far Side is full of amazing scientific concepts. There is this one particular cartoon which I should send you, where the cows, how many of you have heard of Far Side cartoons before? Okay, good. Any of you people who raise your hands, whenever I ask these references, you guys can get very high grades if you just talk to me, because you have the right cultural background. The rest of you need to figure out. Anyway, so Far Side basically, Gary Larson is into cows, as you can tell, because there is Cow Philosophy. And there's this other cow cartoon which I will send you, where the two cows are sitting in their living room, because cows obviously have their living rooms, and then on the phone, the wall phone is ringing, and one cow is looking at the cow saying, there goes the phone again, and here we sit lacking opposable thumbs. Come on, guys. What do you do with the phone if you can't hold it? Right? If you never thought that opposable thumb was so useful for your life, because you had it. If you had it missing, then try to pick a phone without opposable thumb, then you realize what cows felt. As long as the TR function was there, nobody thought T was important to convert V star into pi. It's like, I also need to know plus and minus, it's there. When it's missing, oh my God, how do I convert V star into pi star? There's no way. It's the opposable thumb. Okay? That looks like we nicely painted ourselves to be a really bad corner, but thankfully we did tell you last time that instead of tracking V values, you can track Q values. You can track Q values. Okay? And the Q basically would be saying, if you were to do action A in state S, what is the expected reward you will get? What's the maximum expected reward you can get? And then, of course, if I give you the Q values, V value is nothing but max of the Q values for any state. You see what I'm saying? That's where Q learning becomes interesting. Because otherwise it's your opposite outcome. Transition function went away and you didn't know what to do. Okay? So instead of model-based the TD learning, you do Q learning, which basically works just like TD learning. You're basically nudging Q values to be consistent with their neighbors' Q values, instead of nudging values to be consistent with their neighbors' values. If you do that, then you can do active learning, so you can learn the Q values directly. By the way, this I kind of mentioned it only verbally, but these are the way the equations would look like if you are keeping track of values versus Q values. Okay? In the case of values, the max will occur because the Bellman says the value of a state is the value that its best action will bring it. For the Q values, each action, what's the maximum you can bring me? And then the maxing will be done as and when I need it. And I need to figure out what action should I do in this state. I pick my A with the highest Q value. Okay? So that's basically Q learning. And so this is how the Qs will be this thing. And so anyway, from the point of view of numbers, essentially instead of there being S numbers for S values, if there are S states, now there will be A times S numbers, where A is the number of actions per state. If you are wondering, since I put in this thought into your head that things like swimming will have infinite number of actions, right? That doesn't look good. Infinite times 5 is still infinite. So those cases, you will essentially have to learn QSA as an analytic function. And to maximize the A, then you need to actually use calculus to figure out the gradient, where the gradient vanishes, and say that's the A for which QSA is highest. This is just a little probe into continuous space direction. We won't do any continuous stuff here. Okay, so in terms of Q learning, essentially we do almost the same. Sample now will be RSA S dash plus gamma times max of gamma times the value of that state. The value of that state is max A dash QS dash A dash. Right? This is the only thing that's different. Previously it used to be just the value. It would be max of A dash QSA S dash A dash. So that's your sample. So then Q of SA now will be nudged to be Q of SA plus alpha times sample minus Q of SA. The same temporal difference except now for Q learning. Okay? When you're doing this, that's basically equivalent, you can say QSA is 1 minus alpha times Q of SA plus alpha times the sample. So your weighted average. And so one of the nice things then is if you're doing Q learning, you can nicely, now of course you're actively acting in the world. So remember in the ADP, we said at any given point of time you have a greedy policy.